Sergey Alexandrov from Montpellier, physicist. He will give a mini series, seminar mini series, and the topic is on his first slide, mock modularity of Calabi-Yau threefolds. So, Sergey, please.
Thank you, Jan, and thanks for inviting me to give this series of lectures. So the idea of this, maybe I will switch on the sound of my computer because I hear echo. Let me see how to do it. Yeah. Now it's better. No, it's still on. Strange. Why do I hear echo? Okay, probably I understood. Yeah, now it's good. Okay, so let me start. So the idea of these lectures is to explain you the modular properties of the so-called rank zero Donaldson-Thomas invariants, so more precisely the generating series, and how these modular properties can be actually used to find these topological invariants and also some other topological invariants. This is based on a series of works which I did together with my collaborators. First, my former PhD student Khalil Bendris, then mathematician Soheila Fisbaksh, and physicist Albert Klem, Jan Manschot, Boris Pelin, and Torsten Szymanek. And if you are interested in more details, you can find them in a review which I put to the archive a few months ago. Okay, so the idea is that there will be 3 lectures, and in the first lecture, the first lecture will be essentially introductory. I will just explain some definitions of modular forms and their generalizations. Then we will talk about indefinite theta series, and I also hope to have time to start talking about Donaldson-Thomas invariants. The second seminar will be maybe the most complicated one. There we will study the modular anomaly of the generating series, which I mentioned, and how it can be solved. And finally, the last lecture will be about computing the so-called polar terms, which allow, together with the solution of the modular anomaly, to completely fix the generating series of topological invariants. And also, we will learn about some implications of these solutions. So let's start from the introduction. And first of all, we will define what modular forms are. So in these lectures, I will talk only about modular forms for a cell to Z modular group, which, of course, you know all is just the group of matrices A, B, C, D with integer coefficients which satisfy this relation. And as is well known, this is a modular group of torus, 2-dimensional torus, which means that the complex structures of these torus are parameterized by a complex number living in an upper half plane. The idea is that the transformations like this, A tau plus B, C tau plus D, where A, B, C, D satisfy this relation, they map different complex numbers which correspond to the same geometric torus. It means in particular that if we have some function on a torus or some physical quantity, for example, it must be invariant under these modular transformations. Okay, and well, in fact, as you see from these transformations, the matrices, let's say rho and minus rho, they map tau to the same, let's say tau prime. So in fact, what we should be talking about is not a cell to Z, but P a cell to Z. which is defined as this group with this identification. Well, I'll be sloppy in my lecture, so I will mostly, I will usually talk just about SL to Z. And what we should know also about this group is that it's generated by just two generators, the so-called T and S transformations. So the T transformation is just defined by this matrix, and it just shifts tau to tau plus 1. And there is S transformation, which is given by this matrix, and it sends tau to -1 over tau. And up to relations like S squared equal -1 and ST cube equal also -1. So the group is generated by these two matrices. Okay. Now, let's define what a modular form is. So, as before, we consider tau, variable tau, and I will denote by tau1 its real part, and by tau2 its imaginary part. And since it belongs to the upper half plane, so tau2 should be positive. So modular form is a holomorphic function on an upper half plane. So h tau is holomorphic on h, and we impose an additional condition that it's also bounded at tau2 goes to infinity. So this is one condition, and the most important condition is that it must properly transform under SL to Z modular group. What means properly is the following relation, that once we act by this fractional linear transformation on its argument, then it transforms to itself up to a factor, some standard factor, C tau plus D, to certain power, W, and then we have H of tau. So the W, the parameter W, is called the modular weight sorry, something goes wrong with my tablet. So just 1 second. I don't understand what's going on. So W is the modular weight of the modular form H. And from this definition, it immediately follows that H can be, so H is invariant under T transformations, implies that, I'm sorry, something goes wrong with my tablet. All its keyboard appears on my screen, and I cannot type properly. Okay, I'll try to continue, but I don't understand how to switch off this feature.
So if your keyboard appears and prevents you from writing, just write in the upper half. Probably you can change the page and write in the upper half.
It's impossible. I'm sorry. Something doesn't go. Okay. So h of tau is invariant under this T transformation, which immediately implies that h can be expanded in a Fourier series. To switch off this feature, I'm really sorry. I cannot draw because the keyboard pops up on my screen. You don't see it, but it appears all the time. Very stupid, but I don't know how to correct this stupid feature. Like this. Okay, I'll try to continue. So we have expansion in the Fourier series where I denoted by Q. So this is the standard notation that Q is the exponential of 2 pi I tau. Okay, so I prepared few examples. So maybe the most simple example of a modular form is the so-called Eisenstein series, which is defined as some other, well, all integer pairs of integers of this standard factor, 1 over m tau plus n, and it's very easy to see that it's a modular form. Why? Because if we denote by tau prime this fractional linear transformation, a tau plus b divided by c tau plus d, then it's easy to see that m tau prime plus 1 plus n is the same as m prime tau plus n prime c tau plus d, where m prime and n prime are like this. And it means that you can just relabel the change. You can change the sum over mn to the sum over m prime n prime, and what you get from the denominator, you get the standard factor c tau plus d to the power 2k, which immediately implies that this Eisenstein series is a modular form of weight 2k. Yeah, I should actually add the condition here that this works for k larger than 1, where the sum is absolutely convergent. So this is the standard example of a modular form. And in fact, this Eisenstein series, essentially, they exhaust all possible modular forms because just two functions, E4 and E6, they generate the full ring of modular forms.
Now, maybe you explain, since you're kind of start with basics, maybe you explain the normalization factor, this zeta function. Why do you need it? Or why people need it?
So this is so like
Sergey,
this we
do you
defined
do
what
you
the modular
hear
forms
me?
are. But now
Sergey,
let's consider various. It turns out you see that this definition is very
he does
restrictive
not
because
hear me.
essentially Eisenstein series exhaust all possible modular forms, but we want to consider more general functions. And in the following, we will consider various generalizations of this simple definition, which I just gave to you. And it turns out that all these generalizations, they will be relevant in our story. So let's see how we can generalize. So first, let's write generalizations. So the first generalization will be to relax holomorphicity. So what we can do, we can allow. Yes, sorry. Indeed.
I don't
Just
know
1 second.
but do you hear question? Do you
Yeah.
hear me?
Sorry.
Do
Yeah. Please interrupt me at any moment.
hold on. Do you hear
Can you
me
repeat the
now?
question, please?
Do you hear me now? Do you hear me?
Sorry, I still don't hear it.
Okay, then that's a problem because then it
Just
will
1
be
second. 1 second.
a lecture, but
Yeah. Now I hear. Sorry.
you
Yes.
hear. So then the
Yes.
question was, it's because there are maybe students in the audience. Can you explain the normalization factor, zeta function in the it is in front of the series in the Eisenstein series? Yep.
Uh, yeah. Well, essentially, it comes from terms with m equals 0. So you just put m equals 0, and you remain with the sum over n, and you see that the sum is essentially this zeta function. It just gives the definition of zeta function, and the factor of 2 corresponds that you sum over positive n and positive integers and negative integers.
Thank you.
Okay, so let's go to our generalizations, and the first generalization is that we relax holomorphicity. How? So we allow for a polynomial growth in q to minus 1. So we allow growth in this q to minus 1. And what this means, it just means that in this sum, in this Fourier series, we allow to start our sum from a negative integer. And in this, if this is the case, then the corresponding function h of tau is called weakly holomorphic modular form. Okay. Again, and one more definition is that the terms with n less than 0, they are called polar terms. So in particular, hn with such n are called polar coefficients. So, and as I mentioned at the beginning, they will play important role in our story also. And just to give you again an example, the simplest example of such a function is the so-called inverse discriminant, which is given by this a combination of Eisenstein series. And you see that if you take its inverse, then the first term appears like 1 over q. And this is the simplest example of weakly holomorphic modular form, which has weight minus 12. Okay, so this is the first generalization. So the second one is that we allow for a multiplier system. What is it? So let's go to our definition of a modular form, and our main formula is this one. So let's little bit modify it like this. So let's take this guy, move it here, and let's add in this formula an additional factor. So let's write here certain factor m, which depends on our SL to Z transformation, and we will call this factor multiplier system. So it's given by, so typically it's certain, just some phase factor, which of course should satisfy certain cocycle condition. because we need to have a group law, of course. But why do we add it? Because what it allows to have in this, again, in this Fourier series, it allows to have non-integer powers of Q. And in other words, here we can sum not from minus n, but let's say minus n plus, I don't know, alpha, where alpha is some rational number. And again, just to give you an example, or that this is indeed important, one of the most standard model forms is the so-called Dedekind eta function, which is defined as, you see, 24th root of this discriminant, which we defined before. And it has also some product representation. It can also be written as some kind of theta series. And it turns out that it's a modular form of half integer weight. Yeah, another feature which a multiplier system allows, and I forgot to mention, is that it also allows to have modular weights which are not integers, but also half integers. And this is a typical example of such a modular form. And in this case, so the multiplier system, since it must satisfy some cocycle condition, and the SL to Z group, as I mentioned, is completely generated by just two generators, T and S, it's enough to define this factor M for these two SL to Z transformations. And you see that so this is what this factor is equal to for this for T transformation and S transformation. So this completely fixes the multiplier system. And the Dedekind theta function is one of very important modular forms. It's not all. Then we can also define even more general object, the so-called vector valued modular forms. So what are vector valued modular forms? Well, you just put a vector index on oh, sorry, what happened? Oh, I'm sorry, I don't know what's going on with my tablet. It started reloading, so you still see it, but probably we'll have to wait 1 minute.
Okay.
I'm really sorry. It behaves today in a completely crazy way.
So, and while we are waiting, so all this can be expressed in terms of certain line bundle sections of line bundles, yeah.
I don't know, but why do you need any line bundles? These are
Because the theory of theta functions, it has to do something like a modular forms in general. I mean, it has something to do with powers of line bundles on maybe on the modular curve.
we didn't talk about theta functions yet much. Just we had some
Just in general.
examples. To be fair, I've never thought about such reformulation, but and I don't see why you would need it here. Second. I'm almost there. Mhm. Sure. Um, can you allow me?
So you see, it's funny that this hardware doesn't work well for a talk of a physicist.
Well, the problem is that my tablet is really very old. I wanted to buy a new one before this series of seminars,
Uh,
but it didn't arrive.
you still have time by Wednesday, yes. So it's all right.
So it's here. So let's make it full screen. Okay. Um, so I was about to define vector valued model form. And this is very easy. So we just put a vectorial index, let's say mu, which takes a finite number of values. And it means that also in our SL to Z transformation, we'll have this index here. We'll have index nu here. We'll have a sum of a nu. And we'll have instead of a multiplier system, instead of just being a complex number, now there will be a matrix M mu. So that's a very easy generalization. And again, let me give you an example of such situation. Let's consider a just two-dimensional vector constructed from the Jacobi theta functions. So you know there are four Jacobi theta functions, theta 1, theta 2, theta 3, theta 4. So let's take two of them, and with the argument 2 tau, or in other words, we can also write them as such kind of sum with where mu takes two values, 0, 1. And then one can show that this is indeed a model form of weight 1/2, which is vector valued, and the multiplier system, which is again defined by just two transformations, T and S, it has the following form. Okay, and that's it. Now, and the last generalization, what I would like to consider is corresponds to uh, corresponds to the so-called non-holomorphic model forms. Well, non-holomorphic model forms are again defined in a very simple way. We just allow them to depend on both tau and tau bar. And then in the transformation, so what we do, we transform both tau and tau bar in the same way. And we allow for two factors, we can also put some vectorial index, mu, and we allow for model weight, which consists of two weights, holomorphic and anti-holomorphic. And then there will be the usual sum of a nu, M nu, and finally H nu of tau tau bar. Okay. And again, the simplest example, well, just consider the imaginary part of tau. And it's known that it transforms like c tau plus d modulus squared, which means that this is a modular form of weight minus 1 minus 1. Okay, so very easy. So these are all definitions regarding which we need for modular forms. But now we want to consider even something more interesting.
Sergey, just question. You allow this W to be like rational or something, so the weight doesn't have to be integer, yeah?
So it can be half integer in general. So this requires multiplier system. So if you allow for multiplier system, the weight can be half integer.
Yeah, but if you have two weights, it's something really bizarre because if you have the fractional power of like I don't know, like tau in the power 1/3, that's okay, just a monodromy. But if you have anti-holomorphic part, which is also fractional, I don't know what is it, what kind of functions.
Well, you mean because it's not clear how to define such a complex function?
Yeah, it's a little bit, yeah, it looks like it's not just, a monodromy about the point, but it looks like maybe some sectors should appear with a strange behavior.
I never thought about this problem, but
I mean, if it does not appear in your story, that's okay.
We do have model forms of half integer weight. That's for sure. And we also consider, so now I will define what the mock model forms are. And
Okay.
when we will consider mock model forms, we will also will deal with the idea of modular completions. And they are non-holomorphic modular forms in the sense which I defined here, although with the trivial non-holomorphic weight, namely W bar is equal to 0, but they do have a rational W.
Okay, great. And also I have a question. The very first, the classical definition gives you a ring, which, as you said, it's generated by actually two Eisenstein
Yes.
series. What about generalizations?
Uh, well, I it really depends on the multiplier system. In fact, what is known and will play a very important role is that once we have even vector valued weakly holomorphic model form, with the fixed multiplier system, their space is finite dimensional, which means so they form a linear space, and this space has a finite dimension, and this dimension is restricted from above by the number of polar terms. So these guys, so this capital N here, which means that if you fix somehow, if you know the polar terms of your vector valued weakly holomorphic model forms, you can completely fix these model forms. You don't need to know anything else.
Yeah, that's good, but that's actually also return us to my question about geometric interpretation, because if you have, I don't know, like a vector bundle or some compact manifold, so the space of sections is finite dimensional, so you might get these kind of results for free just from geometry. So
Yeah, probably you are right. Yeah, there should be such an interpretation. But well,
okay.
okay, we will see. So this is just classical things which have been known for many years already. But I would like now to go to a more interesting story about mock model forms. So this is a really much more interesting story, and this is where we already have some modular anomaly in the game. Because what is mock model form? So I will, of course, for the first time, the examples of this mock model forms appeared in the famous work of Ramanujan, but we had to wait almost 80 years until we got a kind of general definition of this object, and this general definition has been given in the PhD thesis of Zwegers in 2002, I think, if I remember correctly. So what is this definition? So what is mock model form? In the simplest case, we again take this holomorphic function on the upper half plane, and what we do, we change its model transformation. So now the model transformation will have an anomaly. So we still have this C tau plus D. Then, okay, if we have a vector valued object, we have this multiplier system with which is a matrix. And then what is important is that so there will be
you missed, yeah, okay, yeah, good.
But then there will be an additional term. There will be an additional term which is defined which is defined by another model form. So I will write it like this: G nu tau bar. No, sorry, not tau. It's Z bar.
Sergey, this part of your page is not visible, so it's
okay. Okay, so I will.
it's integral from what?
Yeah. Just 1 second. I will move it down. I'll move it down probably.
Okay.
Like this. Okay, let me. Okay. Go. Okay. No. Yeah. So the integral from d minus d over c to minus I infinity g nu of z bar and complex conjugated, and then we have tau minus z to the power w dz. So and where g is another modular form of weight weight 2 minus w. And this model form is called shadow. So this is a shadow of a mock model form H. So this is just definition. So if your function transforms in this particular way with some modular form G, then it's called mock modular form. Alternatively, one can give another definition in terms of the so-called modular completion. So what is modular completion? Modular completion is a modification of the original function such that it transforms already as a proper modular form. Usually it's denoted by H hat, and in this case, so And what is important that for mock model form, it's already a non-holomorphic object. So you define it as the original function minus certain correction term. And this correction term is given in this case. It's easy to see by the following integral. So it's just, well, it's the same integral, but from tau bar to minus I infinity, well, of the same thing. Minus z bar dz. And it's called Eichler or period integral. So it's easy to check that given this anomalous transformation, then this function transforms already as the usual modular form of weight W. And you can take it also as an alternative definition of a mock model form, that it has a completion such that it has such a form and transforms as a model form.
So I'm confused because you said that if there is tau and tau bar, then there will be two weights.
Well, it just means that it has model weights like this.
Okay.
So the non-holomorphic model weight is trivial. And the shadow, it can be actually obtained by differential operator. Well, it's again easy to see that this is just 2I tau 2 W and anti-holomorphic derivative of the completion. Okay, so let's go to examples. So the first example is again Eisenstein series, but this very special one, which is obtained from the previous definition if you take k equal 1. So you take k equal 1 in the previous definition, and then you get this the so-called quasi-modular Eisenstein series, which can also be written in terms of this discriminant, which I defined before, and also it has this simple representation. And one can check that it's actually one of the trivial examples of mock model forms. Namely, it's kind of the most basic one, because this is the only example where its shadow is a constant. And of course, constant has model weight 0, so which means that just from the definition, it's easy to see that the model weight of this guy is 2. And model completion, you see, well, it's trivial to evaluate the integral if you integrate constant, this Eichler integral, and it just gives 1 over tau 2, well, with some coefficient, and this is the completion. So this is really like the most basic example. Much more non-trivial example is the so-called generating functions of Hurwitz class numbers. So these are some special numbers in number theory, which correspond to some number of SL to Z equivalence classes of integral binary quadratic forms of some fixed discriminant. Well, also you see divided by the number of automorphisms of this quadratic form. So doesn't matter. So in some way, you can define certain numbers, which are called Hurwitz class numbers. And if you split them in two kind of subseries, so you take h4n, h of 4n and 4n minus 1, and it turns out that 4n minus 2 and 4n minus 3, they are all 0. So you don't miss anything. So you split them in these two subseries, and you define two components, two generating functions. So these two generating functions, they form a vector, two-dimensional vector, which transforms as a vector-valued mock model form of weight 3/2. And the shadow in this case is given by this vector of theta functions, which we had as an example here.
So can you go back and show this formula again? You have here 0. No. Back, I mean, to this. Yeah, you are changing. That's why I'm asking people to prepare to send me slides in advance because you are changing too fast. All right, so you have here H0 and H1. What's in your definition, number of equivalent classes with fixed discriminant? What is 0 and 1 then?
For 0, actually, yeah, there is no. So this number minus 112 is not, of course, the number of equivalence classes divided by something. So you just add this number by hand.
No. It's not
No?
about minus 1.
Oh,
Why you have 2? If you have a collection of numbers Hn, you just form a generating series Hn and the power
yeah.
Qn. So you split them
Okay.
according to
Yes.
their divisibility by what?
Yes. By 4.
By
Well,
4?
yeah. So you see, because
Okay.
here there is 4n, so you actually split them into 4 subseries. But the claim is that 2 of them are trivial; they're 0. So all Hurwitz numbers which correspond to the number 4n minus 2 and 4n minus 3, they are 0.
Okay, let
Just
me.
the fact from about Hurwitz numbers. And then you get these 2 subseries, and the claim is that they form a modular vector.
You see the very definition of these numbers, the one which you said that it's not important, but maybe it is, because it's kind of a Donaldson-Thomas type definition.
Well, the beautiful fact about these Hurwitz numbers is that the function 3h mu, it's the normalized generating functions of Vafa-Witten invariants on P2 for the group SU2. And you see why it should be two-dimensional vector, because the rank of the group SU2 is 2. Sorry, not the rank. So this number, so in general, it's SUN. And for the group SUN, you expect the modular vector to have n components. So for SU2, it's 2.
All right. And so the modularity in physics language correspond to this as duality.
Yes. Yeah.
Okay.
Mhm.
Okay, thank you.
Okay. And sorry. And also two more, two generalizations which I need to explain to you. So first of all, we need to, here I define just the usual notion of mock model form, but we also need the so-called mixed mock model form. Mixed mock. What is it? So mixed mock, it's so as I told you, you can define mock model form just by formula for the completion. So for mixed mock model form, the formula for the completion changes. So you allow the shadow to be given by a sum of products of holomorphic and anti-holomorphic objects. Namely, you can write like this: J, and this star means the Eichler integral as defined here. Then you say that this guy, it has the modular weight 2 plus Rj, and this guy has the modular weight W plus Rj. And then you can see that the total weight is the correct one. So in other words, this is a more general class for which the shadow is given by this Fj, Gj, and here bar. So more general shadow. And it is this class which these mixed mock model forms which typically appear in application. So pure mock model forms almost never appear. You always work in practice with mixed mock model forms. And there is an important fact about these mixed modular forms is that you remember I mentioned that weakly holomorphic modular forms, they form a finite dimensional vector space. So if you compute polar terms, you know the modular form completely. The same is true for usual mock modular forms. So they form a finite dimensional vector space, and moreover, their dimension of this vector space is exactly given by the number of polar terms. For mixed mock modular forms, this is not true anymore. So you do okay. It's still true that with the fixed shadow, they still form a finite dimensional vector space, but there is no kind of it's the so-called Rademacher formula, which typically gives for weakly holomorphic modular forms the form of the function in terms of the polar terms. For mixed mock modular forms, there is no such formula. And as a result, it's not enough to compute the polar terms to get the full function. You need to solve the modular anomaly also in some way. So I will talk about this more later, but the lesson is that, the polar terms are not enough. And another fact why we need mixed mock modular forms, because it is these guys which can be generalized to the so-called high depth mock modular forms. So what these high depth mock modular forms are? Well, very easy. So you just define them iteratively by this formula. You just say that H is a depth, let's say n, mock modular form if its completion is given by this formula, and where G is the usual modular form, but F, or more precisely here you put the completion of F, is a mock modular form of depth n-1. And in this way, iteratively, you define for arbitrary number n. So, for example, depth 0 corresponds to usual modular forms, depth 1 corresponds to usual mock modular forms, and so on. Okay, and the final class of functions which we will need are the so-called Jacobi forms. So what are Jacobi forms are? So these guys, they already depend on two variables, tau and z, where so you can consider them as maps from upper half plane times the complex plane into the complex numbers. And again, you define them as holomorphic functions satisfying two conditions. So what are these conditions? So the first condition is the so-called elliptic property. A squared tau plus 2az, and then here z. And here we have the usual modular transformation, but here we also need to transform this second variable z, which is called the elliptic parameter. And we again have the standard factor c tau plus d, but now we also have another factor, 2 pi m c z squared c tau plus d, find tau z. So you see there is another factor, this exponential, and it's characterized by a new number, m. So we have two numbers now, w, which is the weight, and then m, which is called index of Jacobi form. So if my function phi satisfies these two transformations, it's called Jacobi form of weight w and index m. And of course, yeah, they also can be expanded in Fourier series, now both in tau and z. But what is more important, they due to the elliptic property, they have the so-called theta expansion. So theta expansion means they can be expressed in the following way. 2m minus 1, and here we have h mu of tau, mu of m tau z, where this theta function is some standard theta series given by some like this, q k squared over right, over 4m, and then y to the k, where y is 2 exponential of 2 pi I z. So you see that any Jacobi form can be expressed as finite sum of certain theta series and with coefficients which are modular forms. These are modular forms, vector valued modular form of weight w minus 1/2, because the weight of this theta series is 1/2, so it compensates this minus 1/2. And so this is very important property. And here, of course, I defined this Jacobi theta series in just like I first gave the original definition of modular forms in the simplest case, where it's just scalar function and all weights are integers and no multiplier system, but it has all these generalizations which we had before. You can allow for weak holomorphicity, you can allow for multiplier system, for vector valuedness. Also, you can consider non-holomorphic Jacobi forms, and even you can consider mock Jacobi forms. And in that case, if you consider mock Jacobi forms, you just define them to be the objects which have this theta series decomposition where h mu are mock model forms. And you can also consider high depth objects and so on. Another generalization which you can consider multivariable Jacobi form. So in this case, this z actually is a vector. So it belongs to C, I don't know, M, for example. And in that case, of course, the index is not a number, but in general, it's a matrix. Because you see in this transformation, here, you have things like mz squared, for example, here, or yeah, for example, here you have mz squared, and then you just replace mz squared by, for example, sum over ij, zi, mij, zj. So this is obvious generalization, and one more generalization which also sometimes appears in applications is a generalization to the so-called Jacobi-like forms.
Sorry, I have a question here. Is the H mu a Hurwitz class form? No, right?
No, in general, it's some modular form.
H mu is just any modular form, right?
So if you have a Jacobi form,
yeah,
by definition, from this elliptic property here, yeah, it follows that it has this decomposition with theta given by this fixed formula, where h mu are some functions, and from this modular property, it follows that they must be certain vector valued modular forms.
Okay, I see. Thank you.
Yeah, some vector valued modular form. Which one you well, you don't know, of course, in general.
Mhm.
And if phi is a mock Jacobi form, then H should be mock modular form.
Okay, mock modular form, right? Okay.
Well, if phi is mock also. If it's not mock, then H is not mock also.
But,
So
but the Jacobi form, is a Jacobi form a mock modular form?
No. These are two different notions. So
Okay.
we have modular forms, we have mock modular forms. Then we introduce Jacobi forms, and Jacobi forms have theta expansion in terms of modular forms. Then you can define mock Jacobi forms, which have also by definition theta expansion with coefficients given by mock modular forms.
Okay, thank you. Okay.
So you have Jacobi, Jacobi. So their coefficients just modular. If you have mock Jacobi, their coefficients are mock modular. Okay. And finally, yeah, what I want to define is just Jacobi-like forms. Well, this is very easy. So you just drop this first property, and you don't require them to be to have this elliptic property. Of course, then you lose this theta expansion property. It's not true anymore, but still these are interesting objects to consider, and sometimes they play some role in story. Just to give you a simplest example of such a form, well, it's kind of trivial, 1 over z. Yeah, it's clearly a modular form of weight 1, because you remember z transforms like this. And it doesn't satisfy clearly elliptic property, but still it's evaluated. It's in, sometimes it plays a role, and it can be considered as just simplest example of Jacobi-like form. And just to give you again an example of a true Jacobi form, just take Jacobi theta function. Well, this is a Jacobi form of weight 1/2, index 1/2, and it has non-trivial multiplier system. So, and of course, this is a very important object for many purposes. So 1 hour is over. I told you only half of what I was going to tell you. So I don't know. Should I stop here, or can I?
Probably you should, because if there are people kind of, because I mean in Kansas it's morning and there are morning classes, so then the talk should be 1 hour, maybe plus epsilon, but I believe if since you want to speak about indefinite theta series, it doesn't look as epsilon. Maybe you instead answer kind of a general question. You have already introduced like about 10 different classes. I understand that they somehow will appear as you're generating functions in some particular examples, but besides that, they all will appear in some whatever physics. What's the point? Why this hidden modularity appears in the generating functions which you will consider? Is it kind of physics reason, or there is a mathematics?
Actually, I was going to explain precisely the origin of modularity in our story, namely for this rank 0 DT invariance. I was going to spend some time of explaining this in the beginning of my second lecture, although now it should be shifted probably, because the second lecture will be about then indefinite theta series and DT invariance, and so probably it will be shifted.
Yeah, it's better. You see, it's better not to overwhelm people with. I mean, for those who see it for the first time, it's better not to kind of to bury them under this new definitions for them, new definitions without any motivation. You see, Yes.
Well, the motivation is that all these objects, they appear in both mathematics and physics. And the idea was is that I start with some simple object and then introduce kind of more and more, relax the definition in some way, so that I arrive at the most general object which appears in our story. The most general object being this high depth mock modular forms. So the idea was to arrive at this particular definition.
Yeah, but why physicists are happy or mathematicians should be happy when some whatever mock modular forms appear as a generated? What's special for them? You mentioned that something is finite dimensional if you fix
Yes.
order of poles, so then you can determine your generating function uniquely by imposing restrictions on the poles. What's
Exactly. So the idea is that once you know, well, if you have just a modular form, then, well, it's enough to know the multiplier system, the weight, and then, yeah, you kind of know this finite dimensional vector space where they live in, right? And then if you compute these polar terms, you are done. So you can completely determine your function. So modularity is a way to constrain the function which you want to compute. And mock modularity is well, you see from the definition, it's more relaxed in the sense that you allow for modular anomaly. But still, this modular anomaly has a very special form, so that if you know it, for example, if you know the shadow, then you completely know the modular anomaly. And sometimes you can also kind of solve this modular anomaly and find this finite dimensional vector space where your object lives. And then you can also try to find it explicitly. And that's the idea. So is that we want to determine the modular properties, which will determine for us this finite dimensional vector space. And then we will try to find these polar coefficients or some other data which allow to fix our objects uniquely.
So these
that's
are
the
main purpose is to constrain your generating series so that you can compute it.
Yes, yes.
All right. Okay, so I believe other maybe some questions from the audience. More questions. Well, if there are no, thank you, Sergey, and I remind you to send me, I don't know, PDF file of your notes if your tablet can produce PDF files, and we will post them along with the video, and then we'll meet again on Wednesday, the same time, with your second lecture. All right, thank you.